We're on question number 3. We are graphing quadratics by finding the line of symmetry, the vertex, the x-intercepts, the y-intercepts, and we're going to determine whether the vertex is a maximum or a minimum. Now, the line of symmetry, what is the formula for the line of symmetry? X is equal to negative b over 2a. Remember, the a of the quadratic is 1. The b of the quadratic is that 2, correct? So we take the opposite of b, or negative 2, over 2 times my a of 1. This is the a of the quadratic, the b of the quadratic, and the c of the quadratic. So we're going to have negative 2 over 2, which is negative 1. So the equation for the line of symmetry is x equal negative 1. That would be a vertical line through x is negative 1. If I can let go at the right spot. So we've got our line of symmetry. We know that the vertex lies somewhere on that line of symmetry. So the x of the vertex must be the same as the line of symmetry x. So if the line of symmetry is negative 1, then the x of the vertex is negative 1. Yes. And so to find the y of the vertex, we're going to plug that x in place of x in the equation and solve for y. So we'd have y equal 2 times the x of negative 1 quantity square plus, I'm sorry, you're right, I got ahead of myself. It's going to be x, which is negative 1 quantity square, plus 2 times the x of negative 1 plus 1. We are plugging the negative 1 in place of x, both places it appears in that equation, and we're going to solve for the y. So we'll have y is equal to 1 minus 2 plus 1, which is going to be equal to 0. So the vertex is at negative 1, 0. And we could plot that. And we would be right there, yes. We were solving this. I did 1 minus 2 is negative 1 plus 1 is 0. I could have kept solving down. So y equals 0. Right. And we plot that. We plot that point. So we have our line of symmetry and vertex. And again, in response to the first question, why is the vertex x always the same as the line of symmetry x? It is because the vertex lies on the line of symmetry. Therefore, the x of the vertex and the x of the line of symmetry are the same number. Now, how do we know whether the vertex is a maximum or minimum? A is positive. If A is positive, it opens up. And if it opens up, then the vertex is a minimum. You understand how to determine whether the vertex is a maximum or minimum. So if the A of the quadratic is positive, it opens up. Therefore, the vertex is a minimum. If A is negative, it opens down. Therefore, the vertex is a maximum. And that's in the notes in the first part of this. You just weren't here to get them. That's correct. If it's y equal negative x squared, then the vertex will be a maximum. Correct. To find the x-intercepts are the value of x when y is equal to 0. So to find the x-intercepts, we're going to let y equal 0. So we're going to put the 0 in place of the y. That would give us 0 is equal to x squared plus 2x plus 1. To find the zeros of a quadratic, we can factor the quadratic. We could do the inner head method when a is 1. We could use the AC method if it's not. If we get crazy stuff, then we would have to revert to the quadratic formula. Okay? But if a is 1, then what do we think? We just go ahead and write it down like this if a is 1. And we go ahead and put x, because there's not going to be a 2 on the x or anything. Okay? If a is 1, it's just going to be x and x, not a 2x or a 3x or something. We think, what do you multiply to get c and add to get b? What do you multiply to get a 1 and add to get a 2? You understand that? What do you multiply to get the C answer of 1 and add to get the B answer of 2? And the answer would be a 1 and a 1. Both positive, right? 1 times 1 is 1, and 1 plus 1 is 2. And so then we say either x plus 1 equals 0, or the other factor, x plus 1 equals 0. Subtract 1. Subtract 1. Now, a quadratic has 2 roots, 2 zeros. This time they're identical twins, okay? But they're still 2. So the zeros are -1 and -1. What Miss Ballard would say is that it bounces there. That not really bounces, but it appears twice. It's like it's stacked up on itself. Okay? You have that identical twin result. Now look at where it's at in this particular problem. In this particular problem, it happens to be in the same place as the vertex. And it's setting on the axis. Now we would have known that. Why? You remember if you had a quadratic that dips under the axis and comes back up, the zeros are the x-intercepts. So we would say that it has what? 2 real roots. Zeros are roots. If it is setting on the axis like this one was, we would say that it has 1 real root. It's 1 real root that appears twice, but it's 1 real root. Okay? But what would happen if it never crossed the axis like this? We say that it has no real roots, which means the answers look like what? They have an I in them. Okay? So that's something to remember. We've already solved some that had 2 real roots, and we saw that it dipped under and came back up the axis. It hit the x-axis twice. And then we found one here that has 1 real root, and it's actually setting on the axis. And later we'll find one that doesn't even hit the axis. And finding the roots of that are going to be a little more challenging, obviously. Everybody said we found the roots or the zeros. And then the y-intercept. The y-intercept is y when x is 0. So here we would let x be 0 both places. And if we did, we would have y equal x, which is 0 squared, plus 2 times x, which is 0 plus 1. We let the x's be 0. That cancels, and we get y equal 1. So the y-intercept is at 1, if I can get it in there, right there. That didn't give us a whole lot to look at, did it? So we didn't get a whole lot out of that because a lot of our points were the same point. But we're going to know that this thing kind of, it opens up. We knew that because A was positive. So it's going to do something like that. So it would reflect on the other side doing about the same thing, right? You can make that prettier than I did. Yeah, and we could graph more points. We could actually build a table and get a lot of points. But here we're not trying to get a perfect graph. We're just trying to experience these things and realize, too, that using these things we can get a decent graph but not a perfect graph. So our objective wasn't to be perfect here. If we wanted to be perfect, we would go back to the table building process of page 195A. It's opening our mind up, though, to intercepts and things like that, which is a good exercise here. Any questions on number 3? Okay, number 4. Number 4, to find the line of symmetry, we use the formula x is equal to the opposite of b over 2a. The b was a 2, so negative 2 over. 2 times my a of 1 understood. Understand that? And so we have a negative 2 over 2, which is a negative 1, same as we had last time. So the line of symmetry is x equal negative 1. And I'll draw that vertical line. An equation with x only is a vertical line. The x of the vertex is the same as the line of symmetry x. The x of the vertex is the same as the line of symmetry x. To find the y of the vertex, you insert those x's into the equation and solve for y. So we would have y equal the x of negative 1 quantity square plus 2 times the x of negative 1 plus 4. And so we're going to have y equal negative 1 squared is 1. 2 times negative 1 is negative 2 plus 4. 1 minus 2 plus 4, which is going to be 3. And so the y of my vertex is 3. So I can plot my vertex at negative 1 up 1, 2, 3. And we'll let you catch up with the work there. Any questions on what we're doing? A is positive, therefore it opens up. Therefore the vertex is a minimum. Very good. Okay. It wants us to find the x-intercepts. The x-intercepts are the values of x when y is 0. So we would put that 0 in place of y and solve for x. So we would have 0 is equal to x squared plus 2x plus 4. Now, if we wanted to factor, we would say, what do you multiply to get a 4 and add to get a 2? What can you multiply to get a 4 and add to get a 2? Well, nothing, because 1 times 4 is 4, but 1 plus 4 is 5. That doesn't work. 2 times 2 is 4, but 2 plus 2 is 4. There's nothing that you can multiply to get a 4 and add to get a 2. So it won't factor. So how are we going to find the roots? It won't factor, so AC method wouldn't work anyway. So the in-the-head factoring doesn't work. Therefore, the AC method of factoring won't work. So what's our only other choice? The quadratic formula. If it won't factor, that means we have roots that have square roots in them or imaginary numbers in them, like I. Okay? Okay, so we're going to have to use the quadratic formula. Remember that it is x is equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So we're going to have to plug into that formula to get our imaginary radical roots. So we're going to have x is equal to the opposite of b. B was a 2, so the opposite of that is a negative 2, plus or minus the square root of my b, which is 2 squared, minus 4 times my a, which was an understood 1, times my c of 4, all over 2 times my a of 1. So I'm going to plug into the quadratic formula. There's 3 things I'm going to do here. I'm going to do this, and then that, and then that, all at the same time. That's my first move. Now, we can't just punch this in a calculator because it'll give you an error. It has an I in it. And if it didn't have the I and it was a radical, it'd give you a decimal, which we wouldn't allow. So you have to do it on paper. Okay? And so we're going to have x is equal to negative 2 plus or minus the square root of 2 squared is 4. Now 4 times 1 is 4 times 4 is 16. But when you multiply with an odd number of negatives, the answer is negative. Over 2 times 1 is 2. We're going to finish what's in the radical. And so we're going to have x is equal to negative 2 plus or minus the square root of negative 12 over 2. 4 minus 16 is negative 12. Now, remember that we are supposed to know how to deal with i's, and we're supposed to know how to deal with radicals. If we take square root 12, divide 2, we get 6. Divide 2, we get 3. Remember that there's a pair of 2's and a single 3. From that set of 2's, you would pop out a 2, and the single 3 would go back in. But because it was square root negative 12, from that negative, we pop out an I, and so we get 2i square root 3. But understand how we get 2i square root 3 out of the square root of negative 12. 2i square root 3. And so we have x is equal to negative 2 plus or minus 2i square root 3 over 2. Everybody good to there? Okay. Now, because 2 will go into all 3 of those, then we can divide them all by 2 and get x equal negative 1 plus or minus I square root 3, which would be over 1, but it's still just that because divided by 1 is itself. So my roots are positive that and negative that. Okay, so I'm going to put them in here. One of the roots is negative 1 plus the I square root 3. The other one is negative 1 minus the I square root 3. So we have two imaginary radical roots this time. So how do you plot those? You don't plot those because the coordinate plane is a set of all real numbers. You can't plot an imaginary number there. What does that tell us about the graph? It's not going to cross the axis. Now, A is positive, so it opens up. So we're going to have a parabola that never hits the x-axis, you see. It has no real roots, no real zeros. There's no real place where it hits the x-axis at. Okay? All right. Everybody understand that? So we can't do any plotting from that. And then we want to find the y-intercept. And the y-intercept is the value of y when x is 0. So here, we would replace both x's with 0. And we would have y equals 0 squared plus 2 times 0 plus 4. And obviously the zeros take those out, and we get y equal 4. So the y-intercept is 0, 4, which we could plot. There's the origin up 1, 2, 3, 4. And again, the best we can do just graphing from what they gave us is we could have done a little reflection there, right? With that point, we could have reflected it across, as somebody said a while ago, and try to do a little bit better job. Okay? Any questions there? What we're learning about mainly is how to find line of symmetries, vertexes. Does it open up, open down? Is the vertex a maximum or minimum? How to find the zeros of quadratics. When does the quadratic have two real roots? When does it have one real root? When does it have no real roots? And we'll learn more about that as we look underneath the square root sign. Remember in Algebra 2, you looked at the determinant, you called it, when you looked at just the square root part. And if the square root was 0 inside that square root, that radicand, it would have one real root. If it was a whole number in there, or an integer in there, a positive number in there, then it would be two real roots. Or if it was a negative in there, you knew you had imaginary roots, okay? So we can look just at the thing under the square root part of the quadratic formula called the determinant, and we can determine what the roots are going to look like just by looking at the radicand, the square root of b squared minus 4ac, that piece of it, okay? Any questions on through number 4? Okay? Was that the last one? That's it. All right. Well, you can begin the work on that. Hope you do well.